All right, welcome back, everybody. So I'm going to start off with a couple of announcements, and then we're going to dive into some more linear systems of ODEs. Okay, so I have today's lecture and Friday's lecture online now, so I'm finally more than one day ahead of schedule. So I know what I'll be doing on Friday, and I actually know what I'll be doing next week too now, which is good. On Monday, I'm going to be in California, and so I will not be here, but I'm going to try to get one of my TAs to come, so there will be kind of a question and answer period. You don't have to come to that, but if you have any questions about what we've been doing up until Lecture 5, it might be a good chance to ask for a little more clarification. Okay? Homework instructions, it's been made... It's been brought to my attention that I haven't actually told you how to turn in homeworks. So there's a few ways to do this. You could turn in homeworks in person, just like a stapled bunch of paper in the Friday class. Okay? Or if you want, you can email the homeworks to both of the TAs and myself. Okay? If you do that, please have a reasonable subject like ME564 Homework 1 Submission or ME564 Homework 1 Submission Edge if you're on the Edge online. So there's some of the problems involve Matlab, plots and codes. Definitely include your plots. If you think that there might be some chance of partial credit, you might want to include your code also. But I don't think you, strictly speaking, have to include your code, only if you do something wrong. Okay. I expect all figures to be, adequately labeled, X label, Y label, legend. Like, it should be a publication quality figure, okay? And I'm not looking for a stack of like 50 pages, be reasonable, okay? Okay, good. Homework. I'm out of town on Monday, but I'll be back on Wednesday and Friday. Another announcement. So many of you have probably heard that the mechanical engineering department has a current and ongoing research engagement with Boeing. And so I will be taking either one or two students this year to work on Boeing-related projects. This is kind of a big data meets mechanical engineering project. So we're going to be dealing with large amounts of point cloud data from the wing assembly of an aircraft. If any of you, and there's also 3 other projects, so controls projects and more manufacturing. And so if any of you are looking for research funding or interesting research projects and would either like to work with me or with any of the other professors involved in this Boeing initiative, please send me an email saying, I'm interested, and attach your CV, and we're going to start reviewing them in the next week or 2. Okay? That's all of my announcements. All right, let's start doing some math. Okay. Good. Okay, so what we're going to talk about today, we're going to go a little bit deeper into the harmonic oscillator. So this is a second-order linear differential equation. Okay, so we're going to go into the harmonic oscillator. And we're going to look at 4 different ways to solve this. Okay, so we've already seen a couple of ways of solving differential equations. We're going to think about a couple of more ways, including Taylor series. We're going to guess some solutions and others. Then we're going to look at the damped harmonic oscillator. And the idea is that with the damped harmonic oscillator, we're going to build up to higher order differential equations. Higher order linear ODEs. So instead of just having like x double dot plus x equals 0, I might have, x quadruple dot plus 5, x triple dot plus 2, x dot equals 0, right? I can have a bunch of derivatives and all of their relationships. Okay, so we're going to be building up to higher order linear ODEs. And on Friday, we're going to figure out how to write this in a very general form using matrix systems of ODEs. And next week, we're going to jump into linear algebra, eigenvalues, eigenvectors, and how to really solve big systems of ordinary differential equations. Okay, so that's where we're going. But I want to spend just a little bit more time, so this is most of today, kind of building the framework for when we get into higher order systems. Okay, any questions about what we've done in the first 3 lectures or where we're going? Okay. Okay, good. So last time we had this spring mass system, a mass M, a spring K, and we had our Newton's law, which said mx double dot equals minus kx. Okay. And for now, we're just going to set mass equals to 1, spring equals to 1, because we don't want to deal with any constants. Okay, so we're just going to start with x double dot equals minus x. Okay, and we're going to look at a few different ways of solving this today. Remember, x is just the displacement of this mass from equilibrium. Okay, and at the end of last lecture, we talked a little bit about this physically. This is a really simple system. We can kind of picture in our minds what's going to happen. So if I pull this mass off of equilibrium and let go, it's just going to oscillate back and forth. It's going to swing from positive through 0 to negative. Then it's going to swing back through 0 to positive, and it's just going to keep oscillating. And if there's no friction, it's going to oscillate forever. Okay? So the first method to solve a differential equation is just to guess that you know the solution and try it out. That sometimes works. Some of the best and hardest differential equations were solved by guessing. Okay, quantum mechanics, special relativity, these were essentially really, really educated guesses by very well-informed physicists. Okay? So we're going to guess. And we know that this thing is going to oscillate. So when you think of oscillations, what do you think of? Sines and cosines. Okay? And the first time I made these notes, I messed up. I guessed that the solution was a sine, but that doesn't really make sense. So if I start this thing with an initial condition that's a positive number, and I let it go, that's really more like a cosine, right? I start with something like 1, and then I'm going to eventually go to -1 and then back up to 1. So this is more of a cosine type behavior. So I'm going to guess that x of t equals cosine of t times whatever my initial condition was, x at times 0. That's how much I pull this thing to displace it before letting go. Okay? And if I pull this mass to some initial position x0 and then I just let it go, are there any other initial conditions we have? Any other information I have about the system? The first derivative must be 0. So x dot of 0 has to be 0. Okay, this is an important condition. Okay, so I'm going to take this guess, I'm going to take its derivatives, and I'm going to plug it in and make sure that we guessed correctly. Okay, so x dot time is minus sine t. X naught is just a number, so it just stays out here. X double dot t is minus cos t x naught. And so if I plug in x double dot, I really do have minus x, and so this is a solution. Okay? And just as a sanity check, sine of 0 is 0, so x dot of 0 is 0. This thing starts with 0 initial velocity like we planned it. Okay? Good. Okay, and for general m and k, so for any mass m and any spring constant k, we have x of t is equal to cos. So what's the natural frequency of the system? Sorry. Okay, so the natural frequency is going to be the square root of k divided by m. So we have cosine of square root k divided by m times time times x naught. Okay, so this is kind of the general solution. You could have solved this equally well by assuming that x of t equals cos lambda t, and then solving for what lambda has to equal for this equation to balance. Okay, and lambda would have to equal square root of k over m. Okay, good. That's one method to solve this. Pretty simple. This isn't going to be the best way of solving differential equations. Okay, we want principled ways of solving systems that we don't kind of know the answer already. Okay. Let's see. Okay, so let's do another method of solution. Okay, so method 2. Let's try a Taylor series. Now, this is kind of nice because, right, we're just starting out the 4th lecture of the class, and already you have the basic foundational tools to solve, I would say, 90% of the ODEs we're going to solve in this class, which is using Taylor series. Okay, we're going to derive cleaner, simpler forms of the solution from the Taylor series, but you can always start to solve a differential equation by just assuming that you have a differentiable function, it has a Taylor series, and backing out what that function has to be to satisfy that differential equation. Okay? So this is one of the techniques that should carry with you for the rest of your lives. Okay? This is one of the most general ways of solving a differential equation. Okay? Just assume a Taylor series. That's why I'm kind of hammering it home. It's a little dry, it's a little boring, but when you find yourself, in the qualifying exam or on a desert island, you can always plug in a Taylor series and solve for your differential equation. Okay? Desert island and qualifying exams are actually remarkably similar. Okay, so we assume that our function can be written as an expansion in time. So there's some coefficient constant term plus c1t plus c2t squared plus c3t cubed plus ... Maybe I'll write one more term. Plus c4t to the 4th plus ... If I wanted to write this as plus order, what would the order be? T to the 5th, right? I've neglected everything t to the 5th and higher, so it just gets lumped into this order t to the 5th term. Okay, and I can take the first and second derivatives and then plug it into my formula. Okay, so I'll just do that really quickly. The first derivative is c1 plus 2c2t plus 3c3t squared plus 4c4t cubed plus ... And x double dot is, okay, constant 1 goes away, and I have 2 times c2 plus 3 times 2 c3 times time. Okay, just the chain rule, right? This 2t, t squared, the derivative is 2t, plus 4 times 3 c4t squared, and I'll just write out the last term, 5 times 4c 5t to the cubed plus ... Okay, the second derivative. And now we're just going to set x double dot equals minus x. And we're going to solve for these coefficients and back out what the solution has to be. Okay, so what's the general procedure? What do I do? I don't want this to be like a formula, right? This is supposed to mean something. So I assumed I have a function that I can take a Taylor series expansion of. I've taken its derivatives. I'm going to plug it into the differential equation. Now what do I do? I compare the coefficients. Which coefficients? How do I know which coefficients to compare?
By the order.
By the powers of t, right? So I'm going to start with my constant terms here. And I get, C2 equals 1/2 C0. Okay, good. Then I'm going to look at my first t to the 0 term. So C1 equals 3 times 2 times C3. Sorry? Is there a minus? Minus. There's definitely a minus here. And C3 equals 1 divided by 3 times 2 C1. Okay, we've taken the t to the 1 power and made it equal. The minus comes from the fact that we're making these coefficients equal and opposite. Okay? Good. And now let's just do a couple more. So C4 is going to be, okay, so C4 is minus 1 over 4 times 3 times C2, right? And C2 was minus 1 over 2 C0. So this is, the minuses cancel, and I get 1 over 4 factorial, 4 times 3 times 2, times C0. Does that make sense? If there's any questions, if I'm going too fast, like, please stop me. This is important. Okay? Now, this is almost useful. It's not quite useful yet. How do I really make this expression actually useful? I need to plug in my initial conditions, right? So I have this recursive relationship. I know what C2 is in terms of C0, C3 in terms of C1, C4 in terms of C2, and hence C0. I'll know C5 in terms of C3, and hence C1, and so on and so forth to infinity. But I actually want numbers. I don't want, a constant in terms of a constant. I want numbers. So I'm going to plug in my initial condition. And we have here 2 initial conditions. So let's plug in time 0 into this expression. We get C0 equals our initial position. Okay? X naught is our initial position of this mass. That has to be C0. If I plug in time 0 into my expression for X, I get C0. And if I plug in time 0 into the derivative of position, I get C1. So C1 equals X dot at 0. This is my initial velocity. Okay? And finally, we get, okay, now C2 is equal to minus 1/2 X naught. C3 is equal to 1 over 3 factorial X dot naught. C4 is 1 over 4 factorial X naught, and so on and so forth. Okay? So all of the even terms, C0, C2, C4, are going to multiply initial positions. And all of the odd terms, C1, C3, C5, are going to multiply X dot 0, the initial velocities. So this separates my solution into cosine times my initial position plus sine times my initial velocity. So if I had an initial velocity, it would have a sine component. Okay, so I'm just going to write out the solution over here. C3 should have a minus sign. Yeah, sorry, I keep forgetting my minus sign. This is really important. This would not be sine if I didn't have a minus sign. Thank you for fixing that. So it should go plus, plus, minus, minus, plus, plus, minus, minus, plus, plus, minus, minus forever. Okay? Thank you. So in our problem, we assumed that there was no initial velocity. So we're going to assume x dot naught equals 0. And then all of our terms are x of t equals, okay, we're going to have 1 minus 1 over 2 factorial t squared plus 1 over 4 factorial t to the 4th minus 1 over 6 factorial t to the 6th times x0. Okay, that's just taking all of the terms that had an x0 coefficient. And this function, of course, is cosine, right? This is cosine of t. Let's say I don't want to make this assumption. It seems silly. I just spent all of this time deriving a really kind of general Taylor series expansion. Let's say that I do have an x dot of 0. Then I just take all of my odd terms, And I also have right, C1 is C1 times t. So I have t minus t cubed over 3 factorial plus t to the 5th over 5 factorial minus t to the 7th over 7 factorial times x dot at 0 times my initial velocity. Okay, this is sine of t. So now we actually have the very, very general solution to this problem. Okay? If I have some initial position, so I have my mass, I pull it to some initial position x naught. Let's say I push it a little, so it has an initial velocity x dot naught. Then my general solution is cos t x naught plus sine t times the initial velocity. Okay? This is a lot more general than what we guessed. We just guessed a cosine. This is more general. I wouldn't have guessed this exact form of the solution, so the Taylor series really helped us out. Okay, does this make sense how we did this? Yeah?
Why can't we use the Taylor series like that? I mean, why can't we use, for example, sine and cosine terms in that series?
So why do we assume that x equals powers of a sum of powers of t? Because most of us are familiar with Taylor series expansion, and lots of functions we care about can be written nicely in Taylor series expansion, but you're hitting on a really key point. So the solution that we get for this harmonic oscillator is actually poorly represented in Taylor series. I need all infinite powers of t to capture sines and cosines. And there's a better basis. So this is a basis, constant power, single power of t, second power of t, third power of t. This is a basis for general functions. Okay, so we're used to thinking of vector spaces. Well, this is a basis for a function space. And you can write sine in this Taylor series function space, but it's kind of a bad basis for sines and cosines. So in the future, and probably in 565, we're going to introduce the Fourier transform. And we're going to be writing our solutions in terms of sines and cosines, and sines of 2 omega t's, and 3 omega t's, and 4 omega t's, which are really, really good bases for certain types of physical systems. This is a really good basis for other types of physical systems. Okay? But right now we're just using this because it's very general, it's deeply tied to calculus, and it's something we can use for computations. Okay? Yeah, it's a really, really good question. Okay, other questions about the Taylor series? So if I gave you another differential equation, do you think you could solve it using a Taylor series? Maybe? Okay. Well, what are the key steps? So what's the first step? Sorry? Just say it again. Okay, you could make a guess that it could be written as a Taylor series expansion. Okay? And then, like, if I have x double dot plus 2x dot plus x equals 0. Let's say I want to solve this using the Taylor series expansion. This might be a homework problem or close to a homework problem. So I make a guess that x can be written as an expansion in powers of t. Then what's the second step? Well, I take all of the derivatives up until the highest order of this differential equation. Okay, so I need to take a first derivative and a second derivative. If I had a plus x triple dot, I'd need to take a third derivative too. Okay? So the second step is to take all of the derivatives that I need to capture all the terms in my equation. Okay? I could even have nasty terms like x times x dot. No problem. Okay? We're not going to do that right now, but I could. What's the third step? Set the coefficients equal. Right. So now I know what the... Maybe I'll wait on this case. Okay, so now I take the t to the 0 power from each of these derivatives, and I set all of their coefficients equal to 0. I take the t to the 1 coefficients, and I set all of their coefficients equal to 0, the t squared, and I set all their coefficients, and so on and so forth to infinity, right, dot, dot, dot. And then I can get a recursive relationship of higher coefficients in terms of earlier coefficients. And then I plug in my initial conditions, and I have an entire expression in terms of x naughts, x naught dots, x naught double dots if I have a third order equation, x naught triple dots if I have a fourth order equation, and so on and so forth. Okay? Very, very general procedure. This is kind of the third step is plugging in the coefficients, and the fourth step is plugging in the initial conditions to actually get values for those coefficients. Okay? So I think you should be able to do this now for most differential equations. I'm not going to give you anything nasty like x triple primes or quadruple dots or anything like that. You should probably be able to solve this, so you can practice this as on the homework. Something you could do is a system like this. This is a pretty common one. We'll come back to this one later. So you could take the Taylor series expansion for x dot and multiply it by the Taylor series expansion of x. And you could get your constant terms and your first order terms and your second order terms, and you could actually do the exact same thing for products of x's and x dots and x double dots. And it's a huge pain in the ass, but this is how Bessel functions are derived. Okay, as you actually do this for nonlinear functions, right? This is what people did before Mathematica, when they had a bottle of whiskey and paper. Okay, good. Other questions about Taylor series expansions? So this is on the homework. If you have questions, this is the time.
So when you say on the homework, like solve by hand, this is what you're talking about?
Yeah.
Not some other analytical way of solving?
No, I mean like compute the Taylor series expansion, solve for the coefficients using recursion, plug in your initial conditions, write down the solution. Exactly. Yeah. Yeah.
I know one of the homework problems it asks us to plot, and everything's in terms of variables. Do you want us to pick some initial values and plot those, or just a general?
Yeah, pick some initial values and plot those. Yeah, exactly. Okay, good. I'll do a Matlab example at the end of class. Okay, so I'm going to do two other ways of solving this system. Okay, so the third method is also going to be pretty important, at least for linear systems of equations. So this Taylor series is really what you do when you don't know what else to do. Okay? If you don't know what your solution is and it's not in terms of some simple functions and it's nasty and nonlinear, you can always go back to Taylor series. Okay, so method 3 is another guess. Okay, so what function, when I take its derivative, is equal to itself up to a constant? E to the lambda x, right? So x of t equals e to the lambda t. When I take the derivative, it's lambda e to the lambda t. That's equal to lambda x. Okay, so it's equal to itself times a constant. So all linear differential equations, every single one of them, this one, if I added plus 19x fourth derivative, all linear higher order differential equations are going to have solutions like this. We could prove it, but I don't think any of us want to prove things, right? We're going to see why this is true. And so we're going to guess that this is the solution, and then we're going to derive what lambda has to be. Okay? So we're going to say x dot of t equals lambda e to the lambda t, and x double dot t equals lambda squared e to the lambda t. And so if I have x double dot equals minus x, then I have lambda squared e to the lambda t equals minus e to the lambda t. And this can only be true when lambda squared equals minus 1. Okay, so what does lambda have to be? What numbers 1 squared give me minus 1? And minus I. And does minus I work? Yeah, minus I works. So lambda equals plus and minus I, right? two solutions, second order equation in lambda plus and minus I. Okay, and last time we computed the Taylor series of things like e to the it and e to the minus it, so we know that we can write these in terms of cosines and sines. Okay, so what this means, if we have two solutions lambda that make this work, then we're going to have two terms in our differential equation solution. X of t equals some coefficient 1, maybe I'll make these k's, k1 e to the lambda 1, so e to the it, plus k2 e to the minus it. Okay, that's going to be the generic solution. So I assume that my system has this form. I claim that all linear equations, linear ODEs are going to have this form. I plug it into my differential equation, and I get some equation, some polynomial in lambda that has to be satisfied. And every root of lambda that satisfies this equation is going to be a term in my differential equation. Okay, so this is, k1 e to the lambda 1t plus k2 e to the lambda 2t. Okay, how do I get k1 and k2? Initial conditions? Yeah, okay. So x0. Okay, I'm going to plug in t equals 0 in this equation. What do I get? k1 plus k2. E to the 0 always equals 1. So this is k1 plus k2. Now if I take the derivative of this, I get, ik e to the it, ik1 minus ik2 e to the it. So when t equals 0, what does that equal? Right, I times k1 minus k2. Okay. So these are kind of two equations with two unknowns, k1 and k2. We don't know k1, we don't know k2, but we do know x naught and the initial velocity x dot naught at time 0. Just to simplify the math, I'm going to assume that this is equal to 0, but you can kind of do this for the general case when you actually have an x dot naught. And let's see, so okay, so if this x dot, if my initial velocity is 0, what has to be true with k1 and k2? They have to be equal. Okay, so k1 equals k2. And then if I plug k1 equals k2 into here, I get 2 times k1 equals x naught. So k1 equals k2 equals x naught over 2. Okay, those are my initial conditions. And so I'm going to plug them into here. And I'm going to get x of t equals x naught over 2 times, what's e to the it? Cosine t plus I sine t. And what's e to the minus it? Literally just plug in minus t here. This is an even function, so it's still just cos t. This is minus I sine t. So cos t minus I sine t. My sine it and my minus I sine t's cancel, and I have x naught cos t. Okay, so that's another way of solving this system. This is how we're going to solve all linear systems. Okay, so this is kind of the most useful way of solving linear systems. They're always going to be some combination of e to the lambda t's. So we plug in x of t equals e to the lambda t. We compute all the derivatives we need to, so we get this polynomial in that lambda. And for every single root of that polynomial, for every value of lambda that makes that true, I get another term, e to the lambda 1t, e to the lambda 2t. And I use my initial conditions to solve for what the coefficients outside have to be. Okay? This is how we solve all linear differential equations. Every single one of them can be solved this way. Should we do one more example? Yeah? Okay, I'm going to do one more example, and then we're going to plot this in Matlab, and then we're going to break. Okay, so the third example is kind of cool. So what do we know about spring mass systems? What additional forces do we have usually? Some kind of damping or friction. Okay, so there's some damping D or delta. So there's also higher order terms, right? If I pull a spring too hard, then I start getting nonlinear forces. It's not just K times X. We're going to deal with that later. For now, we're thinking about linear systems, linear models. Okay? So now we have an equation mx double dot plus dx dot plus kx equals 0. This is just F equals ma with a force proportional, damping force proportional to x dot. Okay? And I'm going to divide everything by m, so I get x double dot plus some number I'm going to call zeta. I like zeta. It's cool, fun to draw. Plus omega squared x, right? Because k over m square root equals omega. So k divided by m is omega squared. Just a nice way of writing this. I'm using physics notation here. So this is the system we're going to solve. How do we solve this equation? What do we do? A little louder. We could do a Taylor series, but that's going to be a mess.
Yes.
What's easier? It's a linear system, right? These are all, linear coefficients times my term. So what do? Same thing, e to the lambda t. Okay, so x of t equals e to the lambda t. X dot equals lambda e to the lambda t. X double dot equals lambda squared e to the lambda t. And I'm going to plug it in here. Okay? So what do I get? I get lambda squared e to the lambda t plus zeta lambda e to the lambda t plus omega squared e to the lambda t. So these all had an e to the lambda t that I pulled out into the front. X double dot has a coefficient of lambda squared. X dot has a coefficient of zeta times lambda. And omega squared x has a coefficient of omega squared e to the lambda t. Now, this function is always positive, so it can't equal 0. So the only way this can ever equal 0 is if this equals 0. And when does that equal 0? For what values of lambda does this quadratic equation equal 0? Who remembers the quadratic formula? Who doesn't remember the quadratic formula? It's okay. This is an important one. Okay, so just someone tell me what lambda equals. Minus zeta plus or minus the square root of zeta squared minus 4 omega squared. Divided by 2. Good. Okay. Now, if I have no damping, what does that mean physically? Like, what in this equation, what does no damping mean? Zeta equals 0. Okay, so if I get rid of zeta, what's the square root of minus 4 omega squared? Plus or minus 2 omega I divided by 2 is plus or minus I omega. That's what we expect. That's what we got for the no damping case. So this is at least consistent with no damping. But now this is the most general form. So we can say x of t equals, let's call this lambda 1 comma 2. So the plus case is going to be lambda 1. The minus case is lambda 2. So x of t is going to be some constant e to the lambda 1t plus some other constant e to the lambda 2t. And that's actually the general solution for the spring mass damper system. Okay, so how would I solve for constant 1 and constant 2? Initial conditions. I need to know something about x naught and its initial velocity, and then I could kind of solve for what these have to be. And it's actually going to be really easy. It's going to be exactly the same as those, because at t0, I don't care what lambda 1 and lambda 2 are. Okay? Let's do this in Matlab. Let's plot some solutions. Okay, so it's great to do things by hand, but we all have computers now. So let's use them. I'm going to pull this board down, but you have all of these notes online. Shit. There you go. All right. So the people online can actually hear me cuss much more clearly than you can. I apologize for that. Good. Okay, so we're going to solve the spring mass damper system, just do some numerical plotting of this, see what it looks like, okay? How many of you have used ode45 before? How many of you have never touched ode45 in your entire lives? It's fine. Okay, ode45 is going to be your best friend in ordinary differential equations. Matlab was considerate enough to give you a function that integrates numerically basically any differential equation you can name. Okay? So that's what we're going to do. Clear all, close all, CLC. Probably. Okay. And what we're going to do is we're going to have a natural frequency of 2 pi. We're going to have a damping ratio of 0.25. And then I'm going to define my system. So this is probably pretty important. What I can do is write my system. So I had x double dot plus dx dot plus omega squared x equals 0. And so I'm going to write this as a matrix system of first order equations. This is all we're going to do on Friday. So I'm going to say x dot equals v, some new dummy variable velocity. And v dot is x double dot. This equals minus omega squared x minus d times v. X dot is just v. Okay? And so this is like d dt of x and v equals a matrix times x and v. This is how we're going to solve this in Matlab. Okay, Matlab doesn't like higher order systems of equations. It likes first order linear equations, or nonlinear, but first order. So I'm going to say that this A matrix equals 0, 1, minus w squared minus 2 times d times omega, because I apparently don't like zetas in MATLAB. This is really the d from earlier. Okay, I'm going to use a time step of 0.01 and a time of, I'm going to integrate from time 0 to time 10. And let's pick an initial condition. What should my initial condition be? Okay, I take this mass, I pull it to some initial displacement of what? 2 meters. Good. And I give it an initial velocity of 0 meters per second. Right? Because x naught is 2, v naught is 0. So that's x naught is 2, 0, this vector. Okay. And now we're going to solve this in ode45. Okay, so you can always type doc ode45. And you'll find that this thing returns time and the solution variable x as a vector evaluated at all of those times. I have to give it a function for the right-hand side. I have to give it this function. I have to tell it what time span I want to integrate from 0 to 10, and what my initial condition is. So pretty simple. I give it 3 things. This code is going to be online, so you can play around with it a little bit. Okay, so t comma x is equal to ode45. Now I have to give it a function of x to integrate. That function of x is this matrix A times x. So it's a function of x, and it's equal to, it's a function of time and x, and it's equal to A times x. I'm going to integrate from 0 in increments of dt up to t equals 10. Right, I've defined dt and t. And I'm going to give it an initial condition of x naught. Hope this works. Test ode45. And it runs. OK, good. So my code runs. It integrated this initial condition. I pulled my mass out to 2. I let it go. It should oscillate and damp out to 0. So I can plot t by the first column of x. So look at the size of x. It's 2 big column vectors with 1,001 entries. One for x, the position, and another column for v, the velocity in time going down. Okay? So I can plot t by my first column of x. And this is my position versus time for the spring mass damper system. Started at 2. It swings past 0 to negative 0.8. Then it swings up to 0.4, but it's damping out, so eventually it goes to rest at 0. Okay? This is a little bit quick. We're going to go through this a lot more. Next time we'll go through this again. I can take my higher order system of equations, and I can write it as a system of first order linear equations. And I can solve that in Matlab using ode45. Okay? I think I have 3 minutes if there's any questions about ode45. Yeah, in the back.
The matrix you drew on the board is different than the one you coded up in Matlab.
Did I? Let's call this zeta. And let's just call this minus zeta. Now that's the same. Yeah. Yeah, I think zeta. That should be right. Thanks. The d and the zeta, they're off by a factor of the mass, right? I'm just divided by mass. I probably messed up somewhere in my algebra, but this still should work. Okay? Other questions about Matlab? So this at t comma x is called a function handle. This allows me to define a function on the fly. Okay, so this is a function of t comma x, and if you plug in x, it returns a times x. So I could do this in the command line. I could say f equals at t comma x a times x. And if I said f at time 5 with vector 2, 0, it's going to give me a times that vector 2, 0. Okay, so this is just a nice way of defining functions on the fly in Matlab. Okay, we're going to do more of this on Friday. We're going to deal with higher order systems of equations and put them into matrix form. And then we're going to start talking about linear algebra. Okay, thanks.